Okay. Why? Because this part sensitization and Boolean difference, we can apply that for testing the sequential as well. Okay. So something like we need to again refresh the things about testing of the designs. Okay. At the end, I'll give you the assignment questions. What is the strength that has joined now? So maybe quickly note down the questions for assignment. Then I'll start. Analyze the advantages. Analyze the advantages of positive logic and mixed logic circuit analysis. Analyze the advantages of positive logic, mixed logic, circuit analysis. Explain the concept of universal logic function. Explain the concept of universal logic function for two variables. List out the design guidelines. List out the design guidelines for the digital designs. What are the assumptions / procedures, assumptions or procedures for an efficient design? Explain the elements of design style. Explain the elements of design style. Explain the design guidelines. Explain the design guidelines. So that was two questions. Explain the design style. Elements of design style is one question. Explain the design guidelines is the next question. Okay. So in that, it will be covering your top-down, bottom-up, and mixed style of approaches. Try to explain them also. Okay. Explain the concept of unclocked sequential circuits. Unclocked sequential circuits. Define the need of clocked sequential circuit. Define the need of clocked sequential circuit. Using the concept of, next question, using the concept of mixed logic, explain how to set, reset, using J and K inputs, vice versa. That means both the elements like setting, resetting, using JK or KJ. Okay. Next question. What are the different approaches of realizing ASMs? What are the different approaches of realizing ASMs? That means under that you should be giving traditional approach, mux, one hot, and ROM based. Okay. List out the advantages and disadvantages. List out the advantages and disadvantages. In the same question you can write, because this is related to ASM only.
Okay.
Of each method of synthesis. Of each method of ASM synthesis. Because there and then you can give this. In traditional approach, what is the advantage, disadvantage? In mux method, what is the advantage, disadvantage? Okay. Each person has to take your own example of ASM. Don't try to take it from others. Okay. Take your own ASM, then you write this question. Using any ASM synthesis approach, using any ASM synthesis approach, design system clock, serial bit clock, ABCDs I'm giving. Design system clock A, B is serial bit clock, data conversion. Either you can take serial to parallel or parallel to serial. One is enough. Traffic light controller. Okay. Next question. What is the concept of Wilkes implementation of digital design? So that means Wilkes proposal we are asking. Okay. What is micro programming?
Ma'am, once repeat the last statement, ma'am, before microprogramming, ma'am.
What is the proposal of Wilkes in implementing the ASM? Actually, that question, maybe you can take it up as wide or wide and logic sort of thing, or diode approach. Both the things is proposed by Wilkes. Okay. What is classic microprogramming? I think this question also we asked in mid. What is classic microprogramming? And its advantage in defining the microcode. Explain the microprogramming. Next question. Explain the microprogramming concept using multiple qualifiers per state, single qualifier per state, with a suitable ASM of your choice. With suitable ASM of your choice.
Can you repeat the question, ma'am?
Which one?
This one.
Yes, please.
Correct.
Explain the microprogramming concept with multiple qualifiers per state and single qualifier per state using an ASM of your choice. Okay.
Yes, ma'am. Thank you.
Implement the microprogram controller. Implement the microprogram controller with Muxus and counter as the building blocks. How many questions altogether now?
13, ma'am.
13, ma'am.
15 questions.
Okay. Next one. What is the concept of enhancing the microprogram control unit explain the concept. Next one. Explain the concept of microprogram sequencer. Concept of microprogram sequencer. Uh, 15 questions altogether now. 15.
Yes, ma'am. 15.
So start writing and I'll ask you on any day after you return back to the campus, okay? And we'll go for testing and testability. I think we are left with three major topics. Testing and testability is there. Your MIPS instruction sets are there. And different types of multipliers, adders, and subtractors are there. Okay? Three major topics. Under that, we have a plenty number of subsegments coming over. So once you try to refresh the concept of your combinational logic testing and all. Okay. Let me do this. So testing the combinational and sequential. Yeah, quickly, let us try to take the types of errors what we can test for. Still, you should be remembering them. Struck at 0, struck at 1. So what is the basic definition of struck at 0 and struck at 1? how best you can explain this stuck at 0 and stuck at 1? Ah. How best you can explain them? A simple interview question. Normally, if you people are interested in the core jobs, okay, your Intel or this VLSI based industries, they'll be checking or testing you for this faults analysis. So first basic element what you should be knowing is how many types of errors you have, what is the definition of that, what is the true meaning of stuck at 0 or stuck at 1, how exactly you'll be giving. Already we have seen this in DSD1. When we say that a element or a logic gate or a circuit is stuck at a specific fault, why only 2 we are having? Why only 2, 0 or 1? Quickly. Let it be correct or wrong answer. Whatever you know, you try to speak now.
Is it because we deal with binary?
Yes. So these designs, what we are taking for is using the binary system. So the basic classification we are trying to take is 0 or 1 fault. So the same thing if you want to put for decimal, hexa or octal, it becomes more complex because plenty number of errors will be coming over. That is one basic advantage what we have when we are taking this binary system for all the designs. That this is also one of the reasons why all the digital designs we try to take up with the binary value. Only 2 value system we are able to address all the designs. Okay, so a design what is supposed to be, or a design what is fixed for generating an output 1, rather it is giving a 0, or an design which is designed for a specific value, the complement value if you are getting, we pronounce that a type of fault is happening. Okay, so stuck at 0 means without fault, that circuit should be giving 1. If it is giving 0 means it shows or it appears to be somewhere tied to an opposite value. That is the meaning. Stuck at a opposite value, stuck at 0 or stuck at 1. This is a basic definition. Okay. So now, how many ways you can test them? How many ways you can test them? Different approaches we have seen. Something like it depends on how you are taking or what logic you are using for testing these two. Something like, is it an AND logic, is it an OR logic, or something like combination of this, you are going for NAND or NOR. Okay. So depending upon the type of logic you are taking, we try to have an aspect of what should be the inputs that has to be tied, so that a specific input you want to test or a specific line you want to test. Because why we are saying specific input or a specific line slash path is that your design is not a single input, single output system. Now, a complex design, if you take plenty number of inputs and plenty number of outputs can be there. It that classification, we know that something like single in, single out, or something like multiple in, multiple out, or any cross of single in, multiple out, such sort of thing. But thing is, the complexity is more. You have different number of lines or paths, and you have different number of inputs that is influencing the output. Though we are saying only one single value that will be generated at the output, okay, but many number of inputs or many number of paths or many number of what you say combination of input and path will be deriving your output. Now, such system if you are taking, what is the influence of these inputs or paths if you need to analyze whether the design is perfectly working or not? All the inputs has to be applied, all the outputs has to be derived. Then what is the next step saying that your circuit is working properly? How can you pronounce that? If you know the truthfulness or what you say the truth table for this design. You compare the practical output with the truth values according to the table. If they are similar, we say that they are working properly. If any one combination of input or a path deviation is there, or an input is deriving a wrong output, or combination of the what you say the responses at different stages, maybe if you are taking this as the internal blocks, you have different paths that will be deriving the output from your input to the output. So any segment is malfunctioning, or any path there is a error happening, or there is an influence of what you say the internal segments, then there can be a fault. If such faults you are in a position to identify, then you will be placed as a perfect analytical engineer, okay, testing engineer. So for this, something like if I know what is the input of a segment, or what you say, how many number of inputs I have and how many number of outputs I have, and what are the relations between these inputs and outputs, and what is the logic that is interlinking those inputs and outputs, then as a testing engineer, you can have the assessment of what should be the line that I need to test. In order to have a testing of that specific line, what should be the other inputs that should be given to define a specific output. All this is something like analysis we'll be doing. So what is the logic based on that? What should be the inputs given? I think this also we have seen in the previous DSD1. Say if this line you are testing, this is an AND logic, naturally the definition of AND gate says that any one of the input is 0, the output will be 0, or else something like false if the input is happening, it derives your output also to be false. That means irrespective of the other inputs. Yes or no? If any one of the input is false, we don't need to wait for or something like we say that priority will be like that false will be influencing the output directly. It will derive the fault, whatever may be the other inputs. That is for your AND gate. For your OR gate, if you are taking, that means that something like this. If I need to test a specific line, say this is 1, 2, 3, 4 inputs are there. I want to test on 4th line, means that only the response of the output or only the 4th input should be deriving the output. The others should not be influencing or should not be what you say contributing to the input. So in that sense, make only 4 to derive the output. I cannot make these fellows to be false, because if any one of the input rather than 4 is false, it straight away makes the output to be false. So see that all the other inputs for an AND gate to be 1, okay, logic 1, except the one what you are testing. Then you will be in a position to find the response of the system due to this input alone. Okay. If it is working properly, that means this segment is working properly. Whatever we are trying to define will be achieved here. Okay. So if you give this as 1, naturally all inputs are 1, your output should be 1. Now, if there is a fault on this line, if this is going to 0, it derives this to be 0, means that it is stuck at 0 fault. Okay. Now, if I want to test for circuit 1 sort of thing, if I make this 0, output will be 0. You make that 0, output will be 0. The fourth input is 0. Okay. Now, if any fault is happening on this line, because these are not influencing, the other inputs are not influencing, if it is faulty, means that it is 1, it derives the output to be 1. This is stuck at 1, stuck at 0 and stuck at 1. What is the basic concept is that what is the test or what is the fault you want to find, the complement of that value will be tied to that input. That is a simple logic. Okay, complement of the test what you are taking. So for OR logic, if any one of the input is true, output is true. Now comes how to isolate the other inputs. How? I am testing for this, say, line 3. I want to test for line 3. Line 1 and 2 should be equal to 1 or 0.
0.
0 or false.
Zero.
If it is there, we are making 3 to be contributing to derive the output. Okay, if any fault is happening and say stuck at 0, you want to find what should be the value here?
1.
1. If the other inputs are 0, that means 1 and 2 inputs are 0. Third input is 1. If it is perfectly working, now your output should be 1. If an error happens, it goes to 0. The other way is that if you tie 0 here, it will be 0 if it is fault free. If an error happens, it goes to 1, that means stuck it. So this is what we are mainly focused. Now, taking a complex design, if there is no feedback path, only the inputs and output combination you are taking, say that is a simple combinational logic. Na? There is no, time dependent inputs that are derived back. Say if you take ith stage, if you are taking or some instant you are giving the input, the same instant you will be calculating the output. Now, if no output is fed back, that means your I plus 1 input does not have this ith stage feedback. I plus 1 input is not having ith. Ith means previous influence, then it is a perfect combination. What is the difference in combinational and sequential for us? There will be some parameter of the output that is fed back. There is a parameter of output that is fed back. That means I need to wait for that ith stage output to be generated in order to define what is the I plus 1th stage output. Because this is ith stage, that is previous stage feedback portion, and this ith stage input, in total this will be deriving I plus 1th stage output. How many number of paths are there? That much delay in the sense time duration you need to wait for testing or deriving the system response. So some element of feedback is there. Naturally, we are saying them as sequential. Na? Those are sequential designs. A feedback portion is there. It is pronounced as sequential. Na? Normally, this is the way we are explaining. This is the feedback path. And this is your segment of input versus output. So what is the difficulty level if you are changing or if you are going from combi to sequential is for getting this response, this stage, this response, I need to wait for the previous stage response to be generated. It takes some time duration. Okay, and this is not for one instant we have to test, no? Because here, how many number of inputs we have? Say n number of inputs, you have 2 power n combinations, and say this is m number of feedback paths are there. N plus m, that is 2 power n plus m combination of inputs we need to test. So testing a sequential is very much complex compared to the combinational. So what are the combinational logic testing approaches we have seen earlier? For that stuck at 0 and stuck at 1, we had something like finding out the test vectors. Remember these terms now? Test vectors, essential test vectors. Dictionary. Hope you are able to recollect those things now. What is test vector? A switching function having some set of inputs. 2 power 4 is the combination of inputs. How many number of inputs for which the system is like assumed or while testing found out to be having some error. If for 2 power 4 combinations, if your design is wrongly working, means that your design is flop. There is no need for you to again go for testing or again releasing that into the market. Say out of 2 power 4 combinations, say 1 or 2 combinations, maybe if your design is giving an error, okay, you are having some amount of efficiency. Okay, so what are those 1 or 2 combinations for which a user has to test the design when he is using that? That is test vector. Why we are saying this as vector is combination of that inputs. Out of 2 power 4 combinations, say 4 input design is there, you will be having this what you say, the combination of inputs either in its true or complement form, that combination which defines, okay, the set of inputs that has to be given to the circuit when it is used by the user. Okay. That is called as test vector. Now, what is this test vector or how do this test vector is defined? Or something like what is this essential test vector or what is this dictionary meaning for us? Whatever you remember, tell me. Nothing? You are not able to recollect? Huh. Essential prime implicants, you remember them? That was the beginning portion. Prime implicants, essential prime implicants. The same way we are going for the test vectors. Are you there? People are there? No response for my questions?
fault in the circuit.
Uh, hello. There is no answer. Fault table, you remember? This is what is related to combinational, what I'm asking now. Combinational only I'm asking.
Yes, ma'am. First, we used to check for single line errors, then we make pairs, and then we find.
Hmm.
Am I audible?
Yes, yes, yes.
And then we find for prime implicants like for columns having single ones,
Ah,
and then we uh, make our dictionary in some
hmm.
formats like that.
So how many input lines you have, how many paths you have, that we define that with the line 1 of structured 0, line 2 of structured 0, and so on. With line 1 structured 1, line 1, 2 structured 1. This was your set of what you say, the response of the design. And for that, for which test you are taking, that means this combination, T1, T2, T3, and so on, to how many you will be getting. Okay. In this, our design should have minimal number of test vectors so that our design is perfectly working. If we have to say that our design is properly designed, the number of errors happening in the design should be minimal. Okay. So, this experimentation will give us an information regarding on which line what type of fault is happening. The second subscript says that what is the type of fault, and first says that what is the line. Okay. And corresponding to which test, what is the type of fault happening. I think an XOR operator will be taken for fault-free line with the faulty line, and so on. Okay. And from this, we try to find what are the essential tests that are needed for that specific design. And the dictionary will be giving you the combination of that essential test vectors, defining for that line what is the response of the design that will be coming if it is faulty. Okay. And dictionary is just giving you an information regarding what will be the probable response of the design when a specific test is applied. Okay, that is some ready reference sort of thing. So for that, I think we had some adaptive tree as well as the preset experiments, preset test. Okay, this is branching aspect of pass and fail. And this is product faults analysis, wherein something like what we have seen is two faulty lines can nullify a fault. One faulty line with fault-free line can generate a new fault. That sort of analysis we have seen. Okay, so this is based on the product faults. Whatever may be the experiment you are doing, what is the goal is that find the test vectors in that, find the essential test vectors using your fault table and derive the dictionary. Maybe this experimentation, this aspect of adaptive or preset, it is for a complex designs if you want. Maybe these experiments or these methods will be giving you the effective dictionary, or what you say, the analysis will be perfect. Now, small designs are there, less complex designs. We have this path sensitization as well as the Boolean difference approach. Now, this Boolean difference we can use for complex design also. This is for low to high complex designs, you can use this algebraic method, but path sensitization is for only to some limit of complexity only you can handle this path sensitization. Hope you have to refresh these approaches. Okay, try try to go through your previous lecture notes and try to find out what are those approaches and how you are finding the faults or essential faults. Okay, essential test vector sort of. Okay, so this is something like an introduction sort of thing for the combinational. Where anywhere you see in these approaches, there won't be a parameter of feedback coming into picture because those are pure combinational logic testing approaches. Now, for testing a sequential circuit, what is the method? Testing a sequential design, what is the method? Is that now, if you take the sequential design, what is the difference? Major difference we get is this path is to be analyzed. This path is the major role. That what is the response of the design? Based on that, your new values will be coming in. So this path is important. Now, if purely taking the input and output, like purely observing the input and output, if you take, ignoring the states. Now this is status, no? This is the status of your design. Right? You need to have all complex inputs to be applied. Every input you have to apply. And for every input, its output has to be processed or its output has to be registered. Okay. And what happens is, for such type of testing, you require huge data. All combination of inputs you need to define. And for that, all combination of inputs, you need to define the system response. That is huge data. So, like whether the circuit is functioning correctly or not will be, whether the circuit is functioning correctly or not will be decided by the the responses what you are defining for all input combinations. That approach where all inputs are given and all outputs are taken, we call it as brute force approach. But this approach is not recommended because it needs a huge combination of all the inputs to be applied. Okay, and you need to record all the responses of all the input combinations. Okay, so that approach becomes a little bit, not little bit, it is more complex. The brute force approach is more complex. So what can what can be the remedy or what can be a probable correction sort of thing that we can do in order to cut down this complexity of testing? Is that we for a input sequence means what? Actually, one input means one input will give you two values. No? Sequence means, say, if I take x1, two input, x1, x2, and so on to xn is there. The combination of this 2 power n combinations you are defining, maybe n minus 1 if you start with 0 to 2 power n minus 1. Any one combination of this x1 to xn is a sequence. Okay, you apply this to the circuit under test. Normally we say this is circuit under test, CUT, circuit under test. We need to observe the output sequence. Okay, so if the output sequence is correct, we pronounce that design is perfectly working. Okay, here you need to repeat. If this is one sequence, 2 power n minus 1 such sequences, 0 to 2 power n minus 1, that means all 2 power n has to be applied. And that 2 power n sequences has to be recorded, which needs much of what you say testing time, your memory, like storing that data and all. This is not so recommended approach, the brute force approach. So what is the way to derive these test sequences for a sequential circuit is, this is what you say a sequential thing. You try to convert this into iterative network. A sequential circuit, if you can convert that into iterative network, what is this iterative network means? What is the base logic that is there if you repeat that for n number of times? This becomes your hardware, no? This is your hardware portion, and this is your just what you say an upgradation of status. If you take this D flip-flops, can I put that way? This is the major hardware. All the circuit design components are here. This part is only for what you say updating the status of that design. Na? Can I put that way? This is the status element monitoring the segment. Now, what exactly is this is, say if X is the input, maybe Q, I take it as the output. Q is the output. Oh, sorry. Let me take, normally we take this as Z now. I take this as what you say Q now. This Q portion, the past segment Q will be the present segment Q. So X of I, Z of I take, this becomes say Q I minus 1 will be coming here, and exactly if you take. Am I correct?
Yes, ma'am.
Yeah. So this is the status monitoring segment. So this part is what we need to monitor now in order to find the new values of the output of Z with respect to X of I and Q I minus 1. So this segment, if I repeat for how many number of test sequences I have, if this segment I repeat for how many number of test sequences I have, the sequential design becomes a iterative network. Okay, something like this. Say a circuit under test is nothing but combinational logic circuit. Can I pronounce that way? This combinational logic circuit is the only one fellow wherein what is that changing is we are not changing the hardware here. What that will be changing is the value of X of I and Qi minus 1 only will be changing. And this X of I is external. This is internal. This internal is the one what is generated by the previous external input with the previous response of the design. Hope you understood this. Previous external input with the previous response of the design. That means Qi minus 2 will define Qi minus 1. That will be fed to X of I condition. That means present. That means this Q of I is influenced, or it has an influence of the previous to previous stages also. If this I can monitor, or if this I can handle, that in some what you say stages wise, then the sequential will be turning into an iterative aspect. So circuit under test I am taking. If I feed something like external X of, say I'm putting this, what is that in time? Say if I specify this this element, I should specify this as X of t. and Z of t sequential. This gives me Q of t. Okay, this Q of t plus 1, if I take this as the present response, maybe this I can take this as something like this, Q of t plus 1. So this is in time scale. A sequential circuit is in time scale. Now, if I convert that into iterative, what happens is that becomes time scale becomes the space. In space, we are trying to define the parameter. So x of 0, external input, with Q of 0. Q of 0 means the previous stage input, the previous stage response, previous stage response. This derives what is Z of 0 output. Not only that, the Q of 1. This Q of 1 is given to, this is the repeated circuit. This circuit under test is repeated now. Will be fed with new input of X of 1, okay, with the previous response of Q of 1, which derives Z of 1, Q of 2. Now this is given to see Q of 2, sorry, X of 2. So this goes on. Now what is in time scale, that sequential, is converted into space. So your X of t represents that in that input in time, whereas X of k means this one, X of k, if I put this as k, this represents that in space. If you can convert that, majority of the complexity in testing your sequential designs are gone. That means complexity wise you are cutting down. This is very simple. Now analyzing this is very simple. Okay. Now the next element is the connectivity or distinguishability. What is this connectivity or distinguishability? I think we said that in like the state diagrams, we have seen this term. Two states are said to be connected. Two states are said to be connected, strongly connected. Connected or strongly connected. Sequential designs only. We have this term. Complete system, incomplete system. You
The
have
response of both states are same.
if you give the same sequence of input, same input sequence, okay, to two different states, either S1 or S2, you get the same output sequence, whether it is 0, 1 or 1, 0, whatever it is. Same input applied to two different states, you get the same output sequence. There is no conflict or what you say, there is a difference in the output. Same input given, same output you are getting. We say that two such states are strongly connected, or else they are distinguishable. That was the thing what we have said for two different states. Now, here if you take for the testing sequence, if you are able to like from one state to another state, if you are taking the test, okay, if you are able to connect or reach that state from another state, we say that they are connected, strongly connected. If there is no possibility of reaching, say S1, S2, S3 is there, I have one input, either 1 or 0, it is able to reach this. Whereas this is able to reach here or reach here, or say go this way. Now see here, from S1 you can reach to S2, but not to S3. there is open. Now, there is no such sequence which is connecting this path. There is no such sequence which is connecting the path of S1 and S3. Then we say that it is distinguished. S1 and S3 are distinguished. That corresponding sequence is distinguished. Okay, so such type of tests has to be performed wherein the strongly connected sequences has to be found. Strongly connected sequences has to be found. This resembles or it sounds to be similar for our the state table. The same concept we are taking here also. Okay, just 5 minutes break we'll have here before I go to the testing procedure. Or shall we continue? Varun or Dheeraj, shall we continue?
We'll take a break, ma'am.
Shall we?
Yes, ma'am.
Varun, are you speaking? Your voice is very low.
Ma'am, am I audible, ma'am?
Ah,
We'll take a break, ma'am.
5
Okay.
minutes or 10 minutes, okay?
Yes,
Okay. Okay, we'll start now. So, changing that sequential into your iterative, what is that we are making this feedback paths is that it is set of registers you can imagine. A core under test plus set of registers. What is that set of registers is your D flip-flops or the flip-flops what you are using. The flip-flops what you are using in your feedback. That becomes the registers. Okay. Now, when you are converting this into an iterative setup, what is the logic that will be retained in the sense for every stage is that this circuit under test will be repeated and the set of registers here it will be used something like in and out configuration. In and out configuration means, say, we are having a repetition of circuits under test, we are saying. So this is purely combinational. These two are purely combinational. No? You repeat this how many times you want or how many sequences you have in your testing. Okay, what is that in between you have is you had something like the external input happening and your output defining. Along with that, you had this test of what you say the status element that is being what you say propagated from one level to another level. From one level to another level. So if this is Q of 1, that goes to. Now, in between here, if I isolate or what you say, if I isolate one stage to the other stage separately, the number of registers needed will be more. Okay. In the sense, see here, if I have n bit sequence, I need n D flip-flops. And this n D flip-flops, if I can take that separately for each segment, I need how many n flip-flops is that? M stages if I have, M of n D flip-flops I need. Okay, each stage if I isolate. Rather, if I want to cut down this, I can divide this n D flip-flops in between these segments itself. That registers, these are registers. Okay, in such a way that for this segment they are the what you say intaking, having an input. For this it will be an output. For this segment, this set of D flip-flops will be acting as what you say provider. This is a memorizer. This is provider. Okay, this is in, this is out. So that's why we try to use that in out configuration so as to cut down some what you say number of registers that are used for testing. Okay, so this element or what you say this arrangement of the flip-flops, the set of flip-flops what we had, all this set of this segment is distributed now as in-out configuration between the circuit under test. Okay, and now this segment, like once we are testing something, we need an element or an input segment to dump the input sequence. Okay, to dump the input sequence, then allow this circuit to generate a new output based on the inputs and the test sequence. Next, try to give some sufficient time to generate a new output and new status. Okay, after that, what we do, we try to store this response onto the registers. These registers, these are your registers. And what we do, if you need this testing response to be sent to the next stages, this will be acting as the memory paths or the memory segments. Okay, we try to scan the responses onto the registers, then update this status to the next stage inputs. Like here we have the next set of external inputs now, and try to evaluate its response, then again gather that response onto the registers. That means two operations will be performing. When we are not testing or when we are upgrading the status, two steps. When we are not testing means it's a normal, a sequential response we get, normal sequential response. Some input you give, you get the output, okay? Give some sufficient time in order to have that updation of this Q values from the previous state. You'll be deriving the Z0 and the new value of Q, over. When you want to test, this has to be going to the next stages based on how many sequence inputs you have or how many segments of testing you need to do. So when you are testing, we try to give the sequence, find the response, store that on flip-flops, send it to the next stage. If not, just give the input, find the output. Okay, these are the two operations. That means normal and testing operations. Two operations will be performing on each circuit. See, every time the user won't be testing now. At least at the beginning level, the user will test for the functionality of the circuit. Later, he'll be using that for his own designs. So now here, we can implement this operation of the normal or testing using scan testing approach. Okay, or we can, some textbooks it will give as scan path testing. Both means the same. Scan testing or scan path testing. So, okay. See here, this will be using 2-port flip-flops. What are these 2-port flip-flops is, each flip-flop will have 2 D inputs, okay, 2 clocks. For each 1 D input, 1 clock will be there, and 1 output will be there. Okay, 2 D inputs will be there, 2 clocks will be there to operate these 2 D inputs, and 1 output will be there. So this we try to take as D1, D2, clock 1, clock 2. Okay, so D1 and D2 will be operated according to C1, C2 inputs. Okay, and this is Q output. So such type of 2-port flip-flops will be used. Like I'll give a sample diagram. Say this is a circuit under test CUT. Okay. Normally, if I take, this should be x1, x2, and so on to say x of n. The inputs, external inputs. And this will be deriving, say, outputs Z0, Z1, and so on to Zm, we say. Okay. Now, how many stages or how many test sequences you need, that many dual port D flip-flops will be used. This elements will be used. How many you want, that many will be used. Okay. Now, the first D1, the first D input will take the first Q output of the response. So Q1 plus will give, that means previous response. This gives you the updation value. This is your Q1 that goes back to the system. Now only this segment, if you visualize, what is this segment? Only if this segment. This is circuit under test and one set of D flip-flop. If you visualize this, a simple combi converted into sequential. Previous response with the present input will give you a new output of the status and the output of the circuit. It is one sequential segment. This is one sequential segment. In the sequence you want to test, you take this response to the next level, next stage, in such a way that the value of this previous response, that is Q2 plus, will be taken to D1 and the previous response will be given here. And this is Q2. So this will be going, this is say you take this as P, stage P, QP plus, and this is Q of P. Okay. And here you have D2. This previous D2 will be coming from the first stage dual port. But the first initial dual port D2 will get the sequence that is used for testing. What we call this as is scan data input. Okay. How many bits you are taking, that, or like how many bits you have in this scan data, that many segments you will be having here. Now this clock 1, clock 2, clock 1 and clock 2, clock 1, clock 2, this D2 will be coming from previous stage response. So this is your Q. Okay. Now how do we take these signals? Now is, this is scan data in. When you are testing, you are taking the scan data. This Q is nothing but, sorry, this is Q. This is Q. This is scan data output. And when you are scanning, this is your C1. This is system clock. This is with corresponding to D1. This system clock is corresponding to D1 operation. For D2, it is testing. For D2, it is testing. So this we call it as test clock. This is the general terms that we use. SDI is scan data in, SD out is scan data out. Okay. Now, how is this operation can we put into some steps? First, say I'll put this into some steps now. Okay, scan the test vector Q of I values via SDI, okay, using the test clock. Scan the test data using SDI. SDI is regarding to C2, no? So using this test clock, put the test vector there. Now, this test vector will be applying to along with your X values that are your present inputs, that moment inputs, okay, and give some sufficient time to propagate these inputs along with SDI onto the circuit what you are testing to generate the new values of Z and Qs. These are your outputs generated based on the scan data in and the present value of inputs. Next, what do you do? Apply one SCK, that is system clock. Now apply system clock. When you are applying system clock, what happens is the updation of these Qs happens from the circuit response. Updation will happen from the circuit response. That means this Q plus will be updated when you update through system clock. Okay, and what happens is this updation will make the system to be ready for the next scan data to be applied. Okay, so until you want all the bits tested, that many times you will be flipping between the test clock and the system clock. First one will be with test clock to apply the scan data input, and second system clock is to update the status of the circuit response for the input versus the scan data input combination of response. Now the updation of the new value of output and the status will be done by using the system clock. Okay, you will be repeating this throughout the test vector. Okay, the procedure will be repeated throughout the test vector. Okay, something like first what to be done is when you are testing, this is for testing procedure only. What I am telling is for testing procedure. If it is for normal operation, use the system clock. Use the system clock. Try to take these inputs. The updation values will be already available for the system. So directly you will be getting the the new values of the output with the updated values of the status. Okay, when you are testing, we need to have the scan data input. After the response of the scan data input is generated, then the updation of the status will be happening by the application of a system clock. Okay, this procedure will be like something like you can overlap this procedure of testing and scanning is that, say, first set of scan data in, if you give with test clock, okay, by the time your system updation will be happening for new values of Q. That means when you are applying this system clock, parallelly you can apply this test clock for updating new value on SDI in order to cut down some time there. Okay, that means we can have the overlap of happening of SDI new value applied with updation of the status. Both you can do it at one slot if you apply these two at a time. That means system clock and test clock, if you apply at a time, only the precaution or caution is that your SDI should be ready to be updated here. Okay, if SDI is ready, whenever this system clock is given to update the new response of the status, then test clock will be can be given so that new SDI can be loaded in order to cut down some duration of iteration. Okay, so this is what we call it as scan testing or scan path testing. And if such type of systems, if you have, say, if these test vectors are repeated, or if you have this same test vector applied for plenty number of other circuits. Normally, when this concept, if I take, say, testing of ICs, if you have, testing one IC at a time is better, or testing plenty number of thousands of ICs are better? Which one is efficient way of testing using? Testing one IC or thousands of ICs at a slot? Testing one IC is efficient thing, or testing multiple ICs at a time is efficient? No answer.
One at a time.
One IC at a time. Huh? Normally in industries, ICs, how many number of ICs will be generated in one slot is thousands of ICs. That means because these are prototypes of similar designs. No? IC production, if you take, it won't be one IC per production. It will be thousands of ICs for one lot. In the same way, testing also, if you can test all similar ICs in a lot, that gives you much time consuming, like what you say, time saving, we can say. You are going to save much time if you test more ICs in a slot rather than testing one IC. So normally plenty number of ICs will be placed on the testing platform, and they try to use a controller, what we call it as tap controller. Tap controller means test access port controller. That means, in short, we call it as tap controller. Now, this tap controller will be controlling like when to update this clock or this clock. Okay. So, if there is a controller which can control the slots of initiating the system clock and the test clock, along with the scan data in and scan data out handled successfully between different ICs that are being tested, it is called as, I will extend this. It is called as the scan testing using scan chain. Scan path testing using scan chain. Something we call it as scan chain. Okay. What is the scan chain is? I have different ICs, say same IC same similar IC I'm testing. IC1, IC2, and so on to IC100 or 1000. That means 1000 ICs I'm putting on a series now. Now, what is that we try to take is these flip-flops, what we have used, the dual port flip-flops we have used now here, the same flip-flops we try to take, sorry. You see this type of flip-flops, if you put here in this path, between the ICs, what we are testing, okay, these are flip-flops, these are ICs what I am taking in. Now these flip-flops, See, if this is fed with an external if this is fed with an external input of x of 0, x of 1, and so on to x of n. Okay. And this gives us, say, output of z of 0, z of 1, and z of n. A similar path of these are all flip-flops I'm taking. Now, these are like what we say in and out mode of shift registers we are taking. In and out operation shift registers. Now, see, if these registers are connected 1 to 1 in each stage independently, they form the shift registers for that segment alone. Okay. Now, we have one input that has to be provided to the system. That is the scan data input has to be given. And we need to take the scan data out after giving sufficient time to iterate or for the data to pass through all the flip-flops. Okay. So, these flip-flops, if they are communicating the data to the IC under test and they are storing the data of the response from the IC under test, now this becomes one segment. The same IC, like this register output, I can have the connectivity communicating the previous response, something like this. Now, what is the iteration we are doing? This is updation of queues. This is updation of queues. Here we have done now. Here you had updation of queues. This queues we have updated. This queues we have updated. No? That updation of queues is happening in this path now. This path. Okay. And see here. What is the extra element that we need is a path to scan the data in and take the data out. The scan data input output segment is missing here. So now, if I take an extra other path for the flip-flops, because here you had D1 and D2, one for updating that status, the second one is for having SDI input connected. No? So I'm using this SDI here. And this flip-flop is not only in a position to give its response to the next stage, but also it is ready to give the response to the IC. When it is getting tested or when it is getting tested, this SDI will be provided to the IC that is being tested. If it is a normal shift register, the value of this flip-flop will be going to the next flip-flop. This flip-flop goes to the next flip-flop. That means this is a shift operation. This is testing operation, this part. This will be shift operation. Okay. And this path will go to the next set of flip-flops. Okay. Now this is our connectivity. Scan path using the scan chain. This is using scan chain. Now the last flip-flop gives you ST0. Hope you understood what or how we are testing and storing the data. Both the ways. Testing and storing the data. So this path is nothing but okay, this one. This is your scan chain. Hope you understood this. If you are testing, take that response from the IC. If not, it is a normal shift register. That becomes a normal shift register. Okay, now if plenty number of different ICs we want to, like say this is repeated segments of circuit under test if you are taking, sorry, this one, circuit under test, and this is circuit under test, repeated sequence you are taking. Now, if this is for one IC, if I say, an IC having this much of complexity inside, say if this, I name it as one IC, another IC I want to test, another IC I want to test, plenty number of ICs I need to test, means that I need a segment of this scan registers, okay, and the ICs under test, different ICs. And what else we need is a controller which controls when to test or when to scan. When to test and when to scan. This setup, if I can put it on a representation format, say if this is one IC I am testing, this is another IC I am testing, and such different ICs I am putting in, each IC will have its own scan register. This setup of registers will be there. Okay. This circuit we are putting or condensing that into one block here. This circuit is this one. Okay, this is the expanded version of this one. Okay. And here you have the scan register. I'm putting this scan register means plenty number of flip-flops are there here, which can take the scan data in or the IC status. Both the ways it can handle. Or that means you have to take the help of, to understand, you need to take this setup. Okay. This is scan register. This is scan register. This total chain is there. No? That chain, I'm putting that in a condensed form here. I'm naming this as scan register. All these scan or what you say linked flip-flops, I'm putting that as scan register. It can be 10 to 100, whatever may be the length. It depends on your what you say scan path. Okay. Now, in order to control or in order to have the data that we tested or updated will be decided through the scan registers. That means this becomes, see here, this becomes SDI port, and the last output of that set of registers becomes SD naught for this IC1. For IC2, this is scan data in, where from this input comes is from the previous SD naught. Okay, that means now this is getting linked. Every one IC, what you are testing is getting the scanned information of SDI to SD naught linked in the format of the shift registers. And ultimately, this is your final SD naught of all ICs what you are testing. Okay, and these scan registers will have two clocks, no? Your system clock and test clock. And these two should be initiated or controlled by a controller, what we call it as test access port controller, test controller. This one will be issuing the system clock, test clock, and SDI information, and it will take SD naught information. That means this SDI will be given to the first set of IC scan registers, issuing the corresponding system clock and test clock signals both. Then you can extend this for any number of ICs. Okay. Now ultimately the controller will take the final SD0 information. Based on that, it will be issuing these signals of clock and SDI information. Okay, this is the what we say a scan test configuration using or for multiple ICs. For multiple ICs. So what are the things what we have seen here? Just I try to refresh them. The concept of how we try to test or shift is given using your two-port setup. Okay, wherein test clock will be taking SDI input and the system clock will be updating, or it will be a shifting operation done for shifting the status of your response of the circuit under test. Okay, and such type of this dual ports, if you take them and put it into a path, it becomes the scan path for testing multiple circuits of similar sort with the same test sequence. It is not different test sequence you are giving. So for if you are giving different sets of test sequence for each clock, stage wise the system response will be updated through the scan chain, and this is for repeating or similar sort of ICs. Now plenty number of ICs if you want to test using a tap controller and the scan registry setup, different ICs can be placed on the same platform and you can test all the ICs at a time. This is the scan testing or scan path testing approach. Okay, and something like if a bigger complex design is there, wherein plenty number of ICs are there, different ICs let it be. If you can open your circuits board, maybe if you visualize or if you can see the placing of the components on your board, different components if they are placed, okay, if they are the slots of your inputs and outputs, these are external inputs and outputs. Now these have their own number of inputs and outputs, say. Okay, you can observe these type of the connectivity is happening or saying this is an IC, say a IC or a component, any component if you are taking. This becomes your wiring, and this is your component. Okay. And the connectivities you need to see is from these external inputs to external outputs. These are the things what is available for the external world. Okay. And internally, when I want to test whether this IC is working or this component is working, or any segment malfunctioning or its functionality, if I want to test, normally how the test engineer will be doing is, this is a prototype will be developed, okay, and the components will be mounted and this becomes the wiring, and this will be tested using your CROs and probes, or what you say, your voltmeter or the other meters what are available for measuring. This will be your setup. Okay. Now, I want to test whether this path is working properly or not, or this wire is working properly or not. A wire I want to test. So, what is the general concept is, if the space is fixed, that means this size, if the size is fixed, if the number of components are less, if the size is fixed, the number of components are less, then the wiring space, the space that is available for wiring will be more. That means this wiring width can be wide enough, this can be wide enough so that when I want to test using a probe means a tapping pin. Have you ever seen the probes in your maybe intermediate? Maybe from next week, if you come to the college, we can show you all these things. The probes will have a pin tip. That tip, if you tap on this wire, you will be like measuring the voltage or the parameter under test through the measuring instruments. Either CRO, you can see the display, or the voltmeter or your current meters, you can test how much of voltage or how much of current it is flowing. All this you can test physically. Okay. Now thing is, if the tip size is fixed for the probe, if the space is fixed, the number of components is less, there is a big space available for the wiring. But point is, if the space is fixed, the components are more. More the number of components, less will be the size for available for wiring. The size will be less. That means this should be narrow. The wiring path will be narrow. The width of the wire comes down if the complexity of the design increases. Then tapping using these probes, say if the width of the wiring is very minute, when you try to tap, say this is one wire and this is second wire and third wire, so on. If my probe tip is very wide enough, if my path is wide, there won't be any trouble in tapping that point. But if such type of narrow paths are there, if I put a probe, there is a chance that I may miss the tapping, or I may be shorting the other lines also. This is the practical aspect. If the complexity is more, the wiring space comes down. So naturally what happens is, the width of the wire will be very minute. This is in microns level, wherein your probe tip may not be properly tapping that point, or it can short the parallel lines or other lines which are nearby. So these are what we say the practical, the errors that can happen in while you are testing. So if such a sort of complex designs are there, normally this tapping with probes, we call it as bed of nails test. Bed of nails test, where this probe edge is a nail, if you can think of. This is bed of the wires. The bed of nail test is by tapping the that wire using the probe tip. Okay. So this bed of nails fixture will be failure if the complexity of the design is more. The reason is that the width of the wire will be very minute. There is a problem in tapping the value. Okay. So this high density PCs which have the fine traces of the wiring, we need to have some standardization to test them. So what happened is a group of standard is coming into existence, what we call it as, sorry, ANSI standard. ANSI, I'll tell what is that full form. ANSI, IEEE standard. Another is JTAG. So this procedure, what I said, is called as boundary scan. Boundary scan using the probe tip, testing the points of the connectivities. Okay, so this is followed according to the standard, that is Joint Test Action Group. This is one standard. Okay, and ANSI standard, this one is all these standards are based upon what you say the IEEE, where each manufacturer has to follow these standards and they have to fix what is the size given allowed, and how much of complexity can be handled on that given space, and what is the wiring width that you can have in order to have error-free testing. Error-free testing. This Joint Test Action Group standard, this is adopted by ANSI IEEE standard, and this standard test accessing port, standard test accessing port, and the boundary scan architecture, what I said now, okay, this is confirmed to all IC manufacturers, and these manufacturers will be issuing according to the standard defined by the JTAG group. Okay, and each of the standard will be providing our tap controller aspect, and the boundary scan register, that means BSR aspect incorporated in their IC. Tap controller and boundary scan register. Okay, this has to be a standard, what you say, manufacturing procedure that every IC manufacturer has to follow for their IC product development. Okay, now this using this, having the tap controller and boundary scan register, the setup they have issued is each of the testing will be having a space for the what you say, circuit under test, what we call it as core logic. Circuit under test you can call, or combinational logic you can call. So a general name given for this circuit under test or combinational logic is core logic, and this core logic should be provided with the tap controller. Okay, it should be provided with the tap controller. This setup you can see in any electronic gadget, any electronic board. If you open, you can see this setup there. Okay, this is ANSI JTAG setup. This will be having the tap control. This is the tap controller. Okay, and the set of registers that are used will be placed in the all directions, which are available to both the user as well as the testing circuit. So these are all registers, or what you say, boundary scan registers, BSRs, boundary scan registers. These are all the boundary scan registers which are available. Now, what is the connectivity is that these boundary scan registers can will be used for communicating with the external inputs and outputs, as well the core logic. Boundary scan registers will be in a position to communicate with the external environment. So this I can take. So I can make use of this as one portion of input or output. One segment I can use them as input, one segment I can use them as output. So that's why we are saying this is in-out configuration. Both in-out configuration. As well, not only to the input and output, that means external environment, they will be available. They will be available to the core logic also. So core logic means they should be connected to each segment of the circuit which you are testing. Okay. Normally the wires won't be running in parallel if you see that in practice. Why? Because the induced EMF, if you want to avoid, the wires won't be run in parallel in practice. If you can see this wiring. Okay. So this core logic will be controlled by the tap controller, and the boundary scan also will be controlled by the tap controller. So this tap controller will have the control over the core logic and the boundary scan cell or boundary scan register. All the segments, if you take, it is boundary scan register. Each segment or each thing we call it as boundary scan cell. Okay. Now, for this, something like this. If you take scan data in, this is through the boundary scan register will be communicated as a scan chain. So SD not, SDI, SD not. Some textbook it can give us test data input, and this they can call it as test data output. Scan or test. Okay. Now, the other portion is that this element of the controller should be having a clock input. Now, these signals are external sources. External sources. So this will have 1, 2, 3, 4, 5. What are they is the scan data in external that will be going parallelly to your scan data or through the tap controller. It is a normal operation or testing operation. Based on that, this path will be decided. Okay. And this can be taken as test clock, and this can be taken as the test mode select. This is mode select. This is test clock. And this is test reset. Another control, what we have is scan data out. So this you can have this to the external input. So, I think this is self-explanatory if you can see. This is with the tap controller, what is the setup of your boundary scan registers? So if you can see this boundary scan registers, these boundary scan cells are communicating to the external inputs or outputs. Not only that, they will be communicating with the core logic also. Okay, and the data that is being transferred will be provided by the controller based on the mode that is getting selected. Is it a testing mode or a normal shifting mode? This test mode select will be changing or switching the mode of the IC now. Okay, this setup will be can be used for a normal operation or testing operation. That is the meaning. The mode select will be shifting between normal and testing, and if it is testing, the clock will be initiated. Based on the clock, the SDI will be transferred through the boundary scan, and it will be scanned out at the SD0. Okay. So if you repeat this for n number of times, now you are going to test many number of ICs. Now this tap controller comes out. If such ICs, if you have plenty number of ICs, if you are taking, you can have. What is that to be needed is the tap controller should be provided for every IC now. Okay, and this same TDI, what is that? Say SDI and SD0. This will be coming here, and this SD0 will be coming here as SDI. So this will be SD0. That means plenty number of ICs if you want to test. So a PC board with a boundary scan ICs, if you can open and see, you will be able to observe many number of ICs connected through one line, wherein that line happens to be the scan data path. The scan data path. Where you need them is, nowadays the circuits what are released in the market are having some element called as self-test element. Self-testing means there is no need for a manual test, manual testing procedure to be applied whenever you are using an IC. The moment you switch on, the circuit itself will be testing itself. Okay, that means the tap controller will be issuing what to be given as the SDI sort of thing, and what mode it has to be operated, whether it is a normal mode or a testing mode will be decided, and it will be taking out this IC response that will be monitored with the fault-free response, and it will issue a signal saying that IC is working properly or IC has a malfunction. Okay, self-tests are there now, whatever available now. The present technology is facilitating that self-test procedure. Okay, maybe I'll stop here for today because we need another explanation, much more time. So any doubts are there here, you can get them clarified. Any doubts are there? You can get them clarified. Actually, we will see what is this exact boundary scan cell, this cell, internal structure of that boundary scan. Loosely, we were saying that that is a register. Okay, set of registers only, but the connectivities and the functions has to be thoroughly understood now. It is not a simple shift register we have in this boundary scan. In scan path testing, that was a set of flip-flops we have used. A normal D flip-flops you can take there. But here, there is a combination of a component added, which decides whether the data that is going is to the core logic or to the external environment. The data that is going to the core logic or to the external environment, or is it a transfer between the boundary scan registers itself? That will be decided by the internal setup that we'll take in the next hour. Okay, if any doubts are there, get them clarified, or else we'll close this session. Okay, no doubts, I suppose. I'm closing.